Let's start with number 7. We're going to graph each function and compare it to the parent function. So y equals 3 3x squared. That's it. So we talked about this a little bit in the intro video, but we'll do it again here. Okay, put in x. What do we get out for y? Put in, these are good ones here. Let's just do these 5 points. I'm just randomly choosing these. You could choose anything. You could choose 1.5, 1/4, 100. Anything you choose would be fine. It would be perfectly valid. These are the ones that I chose. So put in 0 here. You do 3 times 0 squared. That's 0. You put in a 1 there. You do 3 times 1 squared. That'll be 1 times 3. That's 3. Put in a -1. That's 3 times -1 squared. -1 times -1 is +1 times 3. Again, is 3. We're starting to see that symmetry again that a parabola will have. Put in a 3. That's 3 times 3 squared. That's 3 times itself is 9 times 3 is 27. And 3 times -3 squared will also be 27. So we will graph this function. So we have 0, 0. Let's choose red here. 0, 0. We need to go all the way up here to 27, so let's make that 27. And each of these will be 9. No, this would be 18 then, wouldn't it? And this will be 9. And each of these little marks will be 3. That'll help us out. So 1, 3. And -1, 3. So 1 and -1. +3. And comma 27. So we are getting big really fast. We're getting really large values for not much of a move over in the x direction. And we will now connect these. Right. Not a great looking parabola, but it'll do the job. This swooping curve thing that just keeps getting steeper and steeper as you go up, and we understand why, because we're squaring these numbers as we put them in, and squaring is a way to get a really big number. You square 5, you get 25. You just go to 6. Square 6, you get 36. That's a pretty big increase. We're just going up 1. So how does it compare to x squared? Well, if you go back to the previous video, you'll find that x squared does not increase this much. In fact, this one increases 3 times faster than x squared does. X squared would look more like, if this were y equals x squared, then we would have 1, 1. That's way down here. 2, 4. That'd be right here. 3, that would only go to 9. And then it would be reflected here. 2, 4, 1, 1. And so we can see that the graph of 3x squared, that red one, is steeper, it's narrower, it's however you want to call it. I would call it actually steeper, because I think of it getting taller, not so much wider, but getting taller this way, and not so much narrower, I guess, not wider, but narrower this way. I think of it getting tall because I think of this as having an effect on the outputs, which it does. So there you go. Our red one there, which maybe this should be red. This one that they've given us is steeper. In fact, 3 times steeper at any given point, at any given x. Okay. So we're starting to hopefully remember, if we've watched the intro video, the effect that that number in front of x squared has for example, number 9, y equals negative 2x squared, x and y. Really like to get a vertical line off of this sometime. There we go. So if we put in for x, we'll choose the same values. You don't have to pick these values at all. You can pick completely different values, as I said before. Now we put in 0, you get negative 2 times 0 squared. That's just going to be 0. That's pretty obvious. And we'll put in a negative 1. Negative 1 times negative 1 is positive 1 times negative 2 is negative 2. Same thing's going to happen with positive 1. You're going to get negative 2 again. Put in a negative 3, you'll get negative 3 squared is positive 9 times negative 2 is negative 18. I was writing the right number the whole time. Negative 18. Negative 2 times positive 3 squared. Positive 3 squared is positive 9. Negative 2 times 9 is negative 18 also. Alright, so let's plot some points. We got 0, 0. We are going to want to go all the way down to negative 18. Okay, so this could be negative 9, and these could be 3 each. Alright, so 1 comma negative 2. So this would be 3, so that would be right about there. Negative 1, negative 2, positive 2. And, oh, sorry, we're going to go out to 3 here. 3 and negative 18. Negative 3 and negative 18. So we see some points there. There we go. And if we think about the graph of x squared, let's say we're to graph it here, there'd be 1, 1. That'd be, let's see, y equals x squared. Remembering that the scale on the y-axis is 3 for every tick mark, so 1, 1, 2, 4, 3, 9. And how's that looking? First of all, the one that we just drew in blue is upside down, right? It opens down. And it looks steeper, and it is steeper. In fact, it is 2 times steeper than this guy here. So it's the blue one. It opens down. You could say it has the same vertex. We could say that it is steeper. I like the word steeper, not narrower. Because narrower draws your mind to a horizontal change, which you could be argued that there was a horizontal change, but I think of it as vertical because it's this 2 here is changing the outputs. And so the outputs are vertical, and there you go. So, yeah, there you go. There's a comparison. There's a graph and a comparison. Let's go to 13. Y equals 5x squared plus 1. Now we're going to add things on. X and y. So we'll put in these tried and true values. They give us a nice spread of different points. Put in a 0, you'll get 5 times 0 squared plus 1. That's going to be a 0 here and give us a 1. 5 times negative 1 squared plus 1. Negative 1 squared is 1 times 5 is 5 plus 1 is 6. 5 times positive 1 squared plus 1. That'll also give us 6. 5 times negative 3 squared plus 1. This negative 3 squared is 9. Negative 3 times negative 3 is 9. Times 5 is 45. Plus 1 is 46. And as these are symmetrical, this will give us a 46 as well. So I'm going to put the y-axis way down here. Or I guess the x-axis way down here. So we have plenty of room to go all the way to 46 here. And this could be 23. And that's prime, so let's see, we could go here. That'd be about 12. And 6 and 3. Okay. So that'll just give us a good idea of where to put our points, just approximations. So 0, 1, that'll be here. Negative 1, 6, that made that easy. Negative 1, 6. 1, 6. 2 and 3. Negative 2, negative 3. Positive 3 took us all the way up to 46. Negative 3 all the way up to 46. Like how fast these quadratics can increase. It can go from way down here to way up there, just with a little bit of a step. We move over 2 and we go up at 40. It's an immense increase. And we'll try and graph this so nicely. That was pretty nice. Just think positively. We did it. Okay, how does that compare to x squared? Well, x squared would go through here. We go through the origin. Through right here. And then again, it's going to be, it's going to go through 1, 1. And 3 is just going to go to 9. I guess 1 would be more like right there. 3 would go up to just 9, not all the way up to 46. And so when we compare the two, we see that our green one is much steeper. So the green one is steeper for sure. It also opens up. Something else that's changed is, look at the vertex. The vertex is up 1. Up 1 unit from where x squared was. And look at why that is. We're doing our whole squared thing here like we have been for the last few problems, but then we add 1. So everything just gets 1 bigger, right? We add on 1 to every output value. This would have been 0, except we added 1 onto it, and so everything's just got that shift up 1. So for what that's worth. Okay. Now we are going to do this without a table of values. We're going to do it with those things we noticed in the intro video, the axis of symmetry, and so on. So let's start with number 24. Y equals negative 2x squared minus 6x plus 3. Okay. When we throw this x to the first power in here, and it's something other than this x squared and this constant, now it changes things. It's not that you may have noticed that we were moving up and down on the y-axis on those previous examples, maybe shifting the vertex up or down, and then making it open down or open up. But now with this this x term in here, x to the first, it'll shift things left and right, basically, and not in exactly an intuitive way that you just look at this and see, oh, it shifts over 6 or something. It's not the way it works. But there is an easy way to find out where that axis of symmetry has moved left or right. And that is from the intro video. You'll remember, perhaps, that the axis of symmetry can be found at x equals negative b over 2a. Okay? Remember, this is always the number that's in front of x squared, the coefficient of x squared is always a. This coefficient of x is always b, and this is always c. No matter what order we write them in, I could write it like this. Still, this is a, this is b, and this is c. Okay. So at negative b over 2a, this is b. Negative b would be positive 6 over 2 times a. A is negative 2. So this is negative 6 over 4. It's negative because we're dividing a positive by a negative. 2 times negative 2 is negative 4, so that makes the fraction negative. So negative 3/2. So when we go to graph this here, we'll find the axis of symmetry is at negative 3/2. So that's, let's say this is -1, -2. This will be negative 3/2. So here is our axis of symmetry. It's that line that cuts the vertex right in half. And since it cuts the vertex right in half, or it cuts the parabola right in half, I've already Freudian slipped here. What part of the parabola is this axis of symmetry going to cut right through? It's going to cut right through the vertex, right through the middle. And that'll be the vertex. Now, how will we find the vertex? Well, just think. We're not exactly sure what this parabola will look like. It might look like this, or it might look like this, or like this, or it might be really steep and way down here. In any case, it's going to be down, and I haven't drawn these very well. These should look like either the top or the bottom, depending on which way they open. It's going to be our vertex. That vertex is on the graph. And any time that we want to find the point on the graph, say we want to find at negative 3/2, where is the vertex? Well, that's just, we've got the x value, we want the y value. How do we find the y value if we have the x value? We just plug it into the equation. So let me get rid of all these. So for one of our x's, we definitely want to put in negative 3/2. That's going to tell us exactly where the vertex is. We know the vertex is on this line of symmetry, and in order to find out where it is, we'll plug it into the function. So that will be -2 times 3/2 squared minus 6 times 3/2 plus 3. And what will that give us? I'm just going to use my calculator. Of course, we could do this. It's possible to do this. So I don't have any problem bringing out the calculator. It just speeds things along. So turn it on. Let's clear that out. -2 times, oh, I should be putting negative 3/2 in here. So negative 3/2. We're going to square that in the parentheses. Minus 6 times negative 3/2 plus 3. And that is 7.5. Okay. Now what will happen when we put in 0? That should be pretty clear. Let me just get rid of this guy here. When we put in 0 into here, let me just erase this other thing. It may be confusing you. Seeing both of these. When we put in 0 into that function, it's going to make this go away. This is going to go away. All that's left is 3. That's an easy one every time. Y-intercept is an easy one. Okay. So here's kind of a cool thing. This cuts the parabola in half, and I guess we should write a few things here. The vertex is at negative 3/2, comma 7. So we'll just go 3, 4. Oh, maybe we should just go like this. 1, 2, 3, 4, 5, 6, 7, 8. Here's 7. So negative 3/2, comma 7 will be right there. That's my bendy axis of symmetry. And then at 0, we have a point at 0, comma 3. And this is it's symmetrical. So we can see that over here the parabola is gonna come down and touch or go through this point, and then it'll keep going and so on. If it's symmetrical, well, this is 3/2 away from the line of symmetry, so 3/2 on the other side, which would put us at negative 3. We should also be at y equals 3. So negative 3, comma 3. Let's just try it out. I'm going to bring this back up, and I'm going to change each of these to just be negative 3. That ought to do it, and we get 3. So we were right. So at negative 3 comma 3, because of that symmetry, we can assume that there's that point. Since we know where the line of symmetry is, and we know that there's a point over here at 0, 3, we can say, well, there must be another one over here just as far away from the axis of symmetry. And that gives us a great skeleton for drawing our parabola. So that's what we'll do, and that's what we did. Okay. Oh, I guess one thing we did not technically do according to the directions is to label these things. So label the axis of symmetry. This is the line x equals negative 3 halves. And the vertex is at x equals negative 3 halves. And y is 7, negative 3 halves comma 7. Okay. Another, just a check, just to know even more so that we have done it correctly. This negative in front of the x squared tells us when a is negative, it's going to open down, and indeed it does. So that should just give us more confidence. We've done each of the steps correctly, and we have the right thing, the right parabola. Now let's do number 29. Pick this one because it's got a negative, it's got a fraction. Terrifying. Alright, so the axis of symmetry, that's what we're going to find first. It's a really useful thing to find. The axis of symmetry is at x equals negative b over 2a. This is b because it's in front of the x. So negative b over 2 times a, which is this negative fraction. Horrific. I mean, terrific. So 2 times negative 3/5 is going to be negative 6/5. Okay. Something you may remember, you may not. It's good to get refreshed right now. If you're dividing by a fraction, it's much easier to multiply this thing you're dividing. So we're dividing negative 2 by this. So instead, let's multiply this by the reciprocal of negative 6/5. So that's negative 5/6. We could do this. We could cross cancel if we like. That'll be a 1. That'll be a 3. So negative 1 times negative 5 is positive 5 over 3. So what's this? This is the axis of symmetry, 5/3. So this is 1. That'd be 3/3. This is 2. That'd be 6/3. So a little shy of 2. We have 5/3. That's terrible. The scale is way off. Much better. So 5/3 would be something like right there, and so we will draw our axis of symmetry like so. Okay, and on our axis of symmetry, we know we should find our vertex, remembering, just briefly, that with this negative a in front of x squared, that's going to make the parabola open down. So it might be here, it might be here, it might be here. We're not sure. How do we find out where it is, which y value it is? We just plug this guy into the function. So x and y. Sure. Okay, so this x value we're going to plug in is 5/3. So we've got negative 3/5 times 5/3 squared plus 2 times 5/3 x, no, that's not x, that is x, we already wrote that as x, plus 2. What will that be? Let's pull out the trusty calculator, let's clear this out. So negative 3/5 times 5/3 squared plus 2 times 5/3 plus 2. Okay. I'm always thinking about this as I put stuff in my calculator that it's going to follow, it's very strictly going to follow the order of operations. If you know PEMDAS, it's going to follow that very strictly. Okay, so first it's going to take this negative 3 divided by 5 and get that answer. And then it's going to multiply it by what you get here in the parentheses, except for you need to do exponents first. So it's going to take 5/3 and square it, then multiply it by this fraction. That's exactly what we want. Now it's going to take 2 times 5 and then divide it by 3, because that's the order of operations, multiplication, division, on an equal level. And that is the same as 2 times 5/3. And then it's going to add 2. So that's exactly what we needed to do. and this is 3 2/3. Right, we could even make it do that, which is also 11/3. Or 3 2/3. This is helpful. Alright, so we'll put this away. 3 2/3. So at our line of symmetry, we'll go up to 3 2/3. We'll make this 1, 2, 3, 4, 3 2/3. That'll be right there. Okay, again, remember, it's easy to find this point that's on the y-axis because if we put a 0 in for x, this is gone, this is gone. All that's left is 2. 0, 2. And then, this is, what is this? This is 5/3. So if we go another 5/3, that's 10/3. So that's 3 1/3. Okay, so from here to here is 5/3. Another 5/3 would take us to 3 1/3. You can verify that yourself. And the reason that's interesting or useful is because this is a symmetric thing. This is the parabolas are symmetric, and so just as far away from the line of symmetry, we should find another point at 2. So at 3 1/3, 3 1/3, or 10/3, 11/3, 10/3. What have I done? 10/3. So I'm going to bring this back up. Might be easier just to go ahead and put it in. Let's just verify that that's going to work. -3/5 times 10/3 squared plus 2 times 10/3 plus 2. And that is a 2. Awesome. Alright, so now we have 3 points. That's plenty to get us going on the drawing of this parabola. There we go. And you could plot all the points you want, and every time, if my drawing were perfect, which is not perfect, but it's pretty good, every time you draw or plot a point, if you put in 1, you should come out with something that looks like it'll probably be a little bit bigger than 3. Every time you plot a point, it will land right on this parabola. And that's what this parabola is. It's basically every point that could possibly be plotted is just squished in there, and they're all touching, and they create this shape. Okay? And just barely enough room for another one before we have to go back to the top. Okay. So, for number 33, it's a rather simple thing here. We just have to say, does it have a minimum or a maximum value? Okay, so if a parabola opens down, it has a minimum value, the smallest value down here. If it opens down, then it has a maximum value right up here at the top. So whether it has a minimum or a maximum is just, is it opening up or is it opening down? Right, this opens up, this opens down. Well, the negative in front of the x squared, the negative a, tells us that it opens down. So it definitely has a maximum. There's a point at the very peak that is the highest point right up there. Where is it? That's what we need to find. Well, we have been finding these values this whole time when we find the vertex. The vertex is going to be at either the highest or the lowest point, depending on if which way it opens. So we're going to find the vertex. That's well, that's going to be a couple of different steps, I guess. What we should actually do is say the line of symmetry. We can find at x equals negative b over 2a. What's b here? What's the coefficient of x? There is no x. There's a 0x here if you wanted to put that in there. So negative b over 2a, that's going to be 0. So the maximum is going to be the y value of the vertex. How do we find the vertex? We put this into the function. Okay, if that's not sounding familiar, go back and watch the last couple of examples where we found the line of symmetry, and then we just took that value and put it into the function. So you put 0 into here, this all goes away, and we're left with -1. So the maximum value is -1. it's weird that the maximum value is a negative, but it's true. If you put in any other value of x, you'll never get a value that's bigger than -1. It'll be -1.5, -2, whatever, so on and so forth. Okay, so first we need to say to ourselves, ask ourselves, does this have a minimum or a maximum value? Does it open down, or does it open up, or does it open down? This negative there, this -a, tells us that it opens down, so it has a maximum value. What is that maximum value? Well, first, it would be helpful to find the line of symmetry. So that's going to be x equals -b over 2a. B is the coefficient of x. -18 over 2 times a, which is -3. This is -18 over -6. This is positive. Not positive 3. So positive 3 is the line of symmetry, so we're going to take this 3 and put it back into the function. So we're going to take this 3, put it in there. That's going to tell us where the y value of the vertex is, and thereby the maximum value of the function. Let's grab our calculator to do that. -3 times, well, 3 squared is going to be 9, plus 18 times 3 minus 5. So the maximum value is -174. That's quite unnerving. Yeah, I must have done something wrong there. What did I not do here? I didn't close my parentheses. Glad to make that mistake for you. Something that could happen to you. So now we've fixed it. We got -3x squared. X squared in this case would be 9 plus 18 times x minus 5. 22. Okay, so let's just erase this silliness here. So 22 is our maximum value. That's the biggest value we'll find on the graph, the parabola of this function. All right. And now we'll do a word problem, and I wanted to do this problem because it's something you could definitely run into in your real life if you owned a store, which you may one day own a store, and this would be something you'd be interested in knowing. This online music store has just kind of taken some observations, and they want to know how they can maximize their revenue, how much money they make. Okay, so this online music store sells about 4,000 songs each day. So 4,000 songs a day. When it charges $1 per song, so at $1 per song. Okay. So let's just stop here and think, how much money do they make in a day? Well, they make $1 a song with 4,000 songs a day. So in a day, they make about $4,000. 1 times 4,000. What if, just hypothetically, now if you charge more for stuff, less people are going to buy it. That's just a fact of life. Well, that's usually true. Sometimes when you charge more for things, people buy more of them because they think it must be better quality. Kind of a weird thing. Anyway, but they know what it is. It's a song. They know what the song is. They know if they like it or not. And if you're gonna charge them more for it, they're not gonna think it's better. They're just gonna think it's more expensive. So few people are gonna buy it. But putting that aside, if fewer people didn't buy it, the same amount of people, 4,000 people bought the song. If it cost $2, let's see, because that makes it an easy way. We just take 4,000 times $2, you'd have $8,000 every day, right? That'd be great, but people aren't gonna buy a $2 song usually. unless they really like it. They have to really like it. And if fewer people really like a song, then kind of like a song. So the moral of the story there is that you just take the number of songs that you sell in a day, and you multiply it by how much you make per song. So, you know, I guess how much you charge for a song, and that'll give you how much you make in a day. So that's cool. So every time it raises the price 5 cents, so for each 5-cent increase, about 80 fewer songs per day are sold. So use the verbal and quadratic functions to find how the store can maximize its daily value, or daily revenue. So it just gives you this function. And it even puts a little explanation in there, but I picked this problem so that we could make sure we understand why each part is the way it is. Okay. All right. So what we're seeing here is, in this part it says the price per song, dollars per song. Does that make sense? Well, it starts out as $1. That's what it says in the verbal model. That would be what it says in the word problem itself. It starts out at $1, and we're going to add on a certain number of 5-cent increases. So X 5-cent increases. If we add 2 of these, we'll have a 10-cent increase. Add 4 of them, we'll have a 20-cent increase, and so on. So that part makes sense. This is the price. Okay. I guess we should write price here. So we take the price times the number of songs. Perhaps this is the number of songs. They say for every increase of 5 cents, which is what X is representing, for every increase of 5 cents, we'll sell about 80 songs less. So you take 4,000 and you subtract 80 for every increase of 5 cents that you make. So if we increase it by 5 cents, then we'll sell 80 less songs. If we increase it by 10 cents, that's 2 increases of 5 cents, we'll sell 160 less songs. So it's, you know, it really is something you could use if you have a store for a few years and you just mess with the prices a little bit here and there, and you notice the trends over a long time. You could set up a model just like this and see how you might maximize the amount of money you make, because you may lose customers, but you make more money each song. So yeah, that's the kind of the dilemma. How much do you increase that before, you know, you're making this much money at $1 a song, and you increase the price and you start making more money, but fewer people are buying it. You increase the price, you're making more money per song, but few people are buying it, fewer people are buying it. And right about here is where you see you top out in your revenue. Fewer people are buying it, but you're making more per song, so overall you're making more money. Okay? So that's what we're looking for. We're looking for where does that function top out. And so that's going to be a parabola. And that would just work out to, you know, multiplying this out. This is the number of songs. Multiply this out. It's a quadratic model. Write it in standard form, and then do everything we have been doing. So we've got the distributive law on our side here. So 1 times 4,000, that's 4,000. Plus 1 times negative 80x, so that's minus 80x. And then we do these guys here, distribute this 0.05x. 0.05x times 4,000. And that's, I always run for my calculator when a weird thing like that is, and that comes up. So 0.05 times 4,000. That's 200. So plus 200x, and then the 0.05 times negative 80. It's negative 4. So negative 4x squared, because we're multiplying the x by the x, and we get x squared. This would be 4,000 minus, or actually plus 120x, negative 80x and 200x, minus 4x squared. Okay, remember we're imagining that we're charging more per song, few people are buying it, and at some point we maximize how much we can make each day. So we're looking for the vertex, basically, of this parabola. So we're going to look for the line of symmetry. That's x equals negative b over 2a. This is b, so negative b over 2 times a. A is the guy in front of x squared. Negative 4, so this is negative 120 over negative 8. And so negative 20 divided by negative 8 is 15. Okay. So what is 15? 15 is x. X is the number of 5-cent increases. Okay. So how much should we charge per song? That's the question. We should go up 15 increases of 5 cents. So our cost per song should be 1 plus 0.05 times 15. That would bring it to $1.75. And if we're making $1.75 per song, you know, this is telling us our revenue, how much money we're going to make. We could just put 15 in here. And when we do, yeah, let's go ahead and do it. We're going to put 15 in there for x. We're going to see 15 increases of 5 cents. So here in the first parentheses, we have 1 plus 0.05 times 15. Let's put times 15. Okay, so that's the cost of each song. That's that part of it. Times the number of songs that we sell in a day. That's 4,000. Minus 80 times 15. We're going to lose 80 customers every time we increase the song price 5 cents, and we are going to do that 15 times. So now we hit enter, and we should make $4,900 a day. So R of 15, if we let the x be 15, that's 15 increases of 5 cents, we should make $4,900 a day. So we don't have as many customers, but we're charging more per song, and we're making $900 more than we were. Okay. That is it. That was 55. If you hadn't figured that out by now, should have written that. Hope that was helpful. Let me know if you have any questions. See you later.